a nice, fun thing to look at. But let's just pull back from this. We'll talk about what's happening in terms of why you would draw a picture like that. I got these two pictures of waves, and what we're looking at down here actually are two sources. You imagine them being ripples on a pond. So we'll think of them as wave sources, okay? And so what we're talking about is wave sources. It kind of reminds me of water waves, but it's actually going to represent light waves for us. So if we had two wave sources, let's just say that they were, I don't know, we could actually take a black piece of paper. And if we were to slice a really narrow slice here and a really narrow slice here and shine the same light at the back of this paper, can you imagine that the light would ripple out through these holes? And it really does act like water waves. And the same thing would be true for water. We could actually take a wall in the water and you could cut a notch in that wall. And if there were waves coming in from the ocean, they would lap up against that wall. And you can imagine in like an interior harbor, there'd be these ripples rippling out into the harbor. You guys can picture that probably, right? In fact, not too far away from here, there's a duck pond. And the duck pond, I think it's to the east. There's a duck pond that has a couple of openings for ducks to swim in through. And then there's like a beach over on this side. And then the ducks can kind of paddle around in here. It's almost like a little safe harbor for ducks, right? And it's like a cute environmental thing, sure. And they can build their nests and everything. But this is like water waves, but it's representing for us light waves. Anyway, what we remember from our investigations into sound and waves previously is that if I have two waves that happen at the same spot at the same time, they experience superposition. Superposition means that when those two waves happen at the same spot at the same time, I'm going to count it 1, 2, 3 units of amplitude, 1, 2, 3 units of amplitude. I could take a slice and I could say those two functions add up. And we just had one of our favorite math teachers pop his head in the door and he asked if we were going to be talking about waves today. And here we are. Yeah, we're talking about waves. If one of my favorite math teachers was talking about this, he would say f of x plus g of x equals h of x or something like that. Can you imagine him saying that? Now, if f of x and g of x are the same function, I would say that g of x is just 2 times f of x. Agreed? That makes sense, right? Now, I'm not using that notation, but I am going to use that thought process. If f of x plus g of x gives me 2 times f of x, then amplitude of 3 plus amplitude of 3 is going to be 1, 2, 3, 4, 5. Amplitude of 6 at that point. If I slice it here, amplitude of -3 and -3 will give me 1, 2, 3, 4, 5, 6 amplitude at that point. And it would kind of repeat if these two waves are lined up with one another. Now, when we say that they're lined up with one another in physics, we use the word in phase. And my math friend might also use the word in phase. And he would mean the same thing, but that would be the sum of those two functions. And my math friend would say f of x plus g of x equals h of x. For me, I'm just going to say wave superposition. Wave 1 plus wave 2 gives me the waveform wave. That's the resultant, okay? The superposition wave. If I have these two waves phase shifted, now specifically in this case, we're talking about them being phase shifted by half of a wavelength. Now my math friend would talk about them being phase shifted by how many radians? Oh, is it pi radians or pi over 2 radians? How many radians in a complete cycle? 2 pi's. So if we're being shifted by half of a cycle, half a wavelength, how many radians have we been shifted? Pi radians. So yeah, my math friends would say that these guys are phase shifted by pi radians. I'm going to say that they're phase shifted by half of a wavelength. We're all saying the same thing, but with a little bit of a different accent, okay? Some of my math friends would say they've been phase shifted by, what, 180 degrees or 360 degrees? 180 phase shift, right? So depending on whether we're talking about radians, degrees, or in physics, raw wavelengths, right? So half a wavelength phase shift, okay? All the same thing, okay? So 180 degrees. Anyway, the idea here is if I take a slice, now I've got, I don't know, let's call this our new f of x and our new g of x. If I've got a positive amplitude of 3 and a negative amplitude of 3 at the same spot, that's going to be total cancellation. negative amplitude 3, positive amplitude 3, total cancellation. In fact, if you take a slice anywhere along the line here, what you're going to find is that f of x plus g of x, or wave 1 plus wave 2, completely cancels out. And that's kind of a neat property of having two identical wave functions that are phase shifted by half of a wavelength, is that they're going to cancel each other out. Now, there's a name for this. What's the C word for the first one? You learned it in sound and waves. Constructive, yeah. This is constructive interference. And this guy here is destructive interference. I'm trying not to dip below my diagram because I got to use this white space for something maybe. But constructive interference and destructive interference. Another thing that I think about when I think about waves is just this idea that if I have a wave that comes from a single point and I'm thinking about a two-dimensional universe, those waves would ripple out as a pond, or as same way as ripples on a pond. I'll just say like ripples on a pond. And we have kind of a coding thing that's going on here, and the code goes like this. When we're drawing these ripples on this, fictional pond, the solid lines are the crests or the peaks, and the dotted lines, you guys remember the T word? Troughs, yeah. And so people sometimes talk about maxima and minima. Another thing that we talk about is, hey, if those lines are crests or peaks and the dotted lines are troughs. And when I say crests and peaks, this is a crest on a side view, a profile view of a wave, and this is a trough. Okay, just so that we don't have any doubts about what we mean by crests and troughs. But what we just said was that when crests overlap with crests, you get supercrests, constructive interference. When crests overlap with troughs, you get not super troughs, you get destructive interference. You get obliteration. But if I look at this from overhead, it seems to me that a trough could arrive at another trough from two different wave sources like this. Can you imagine there's a ripple coming in this direction and a ripple going in this direction, and they meet each other? That means that they would be a crossover point here. Likewise, there could be a peak meeting another peak, a wave front as viewed from overhead. That would produce constructive interference. And then I guess if that's true, it must be true that when a trough meets a peak going this way, or when a peak meets a trough going this way, you get destructive interference. Okay, so now we're shifting our thinking from being a side view of a wave to being an overhead view of a wave, but we're not letting go of the idea of constructive interference and destructive interference. Is everybody cool with this idea? Essentially, on the left-hand side, we have a one-dimensional description of a wave, along a timeline, if you like, or a spatial line. Now we're trying to up our dimensionality to 2D, okay? Of course, it's actually 3D because the fact that I'm saying peak and trough while looking at it from overhead means it's coming towards us or away from us, right? So with that in mind, I want to come down here to this picture. And in the past, believe it or not, here, I'll flash it up on the screen. In the past, I've made people draw this themselves. And you guys got it for free because I spent an hour in Google Drawings one day and did a bunch of concentric circles. Believe it or not, this took longer than I wanted it to. But I did get all the lines. Notice, I got all the lines for these concentric circles to more or less line up with the grid in the background. Can you see that each one of these concentric circles is just about lined up with my grid? Maybe I got some fine tuning to do, but just appreciate. Can everybody say ooh? And then say ah. Thank you. That's beautiful. All right. So that really was a little bit of effort. But what we get out of this is these concentric circles rippling out from 2 point sources, very much like the ripples coming out from one pebble that would get dropped into a pond, okay? But like I said earlier, these point sources actually for us, because we're in a quantum and electromagnetic waves unit, are representing the sources of light, rippling out into space from 2 point sources. And we're going to say that these waves are in phase. with one another. One another at some points, not at all points. So let's figure this out. What we said earlier was that when troughs and peaks meet, there's going to be destructive interference. And so I think for that, I want to grab my pink highlighter and I want to put a dot everywhere where a peak and a trough meets. And so I'm going to be kind of intentional about this. I'm going to look for peaks and troughs. I'll be systematic about it.
Sorry, we're placing a peak dot where?
Wherever a peak and a trough meets, wherever a solid line and a dotted line crosses. Everywhere a solid and a dotted line crosses. And because these are not actual ripples of water, they're just drawings that I did in Google Drawings. Things aren't exactly perfect, but they're pretty darn good. Because what I'm starting to see is that these peaks and trough crossings seem to happen in lines. Like I said, I just did this drawing probably a couple months ago, but this is the first time I'm using it with a class, and I'm actually kind of glad that everything's working out. Not that there was really doubt, I'm just saying. All right, as I look at this, trying to find anywhere else that I can get it to work, hunting around where the crossings are happening. Maybe I missed one over here. There you go. Got a bunch of lines. Maybe I'll make a little legend for myself. Everywhere where there's pink is where destructive interference happens. Now I want to take a second and I'm going to pull out my blue highlighter and I'd like to put a dot everywhere where a solid line crosses another solid line or a dotted line crosses another dotted line, because according to the earlier talk, that means that constructive interference is going to happen at those points in space. That's when they're going to be in phase with one another. But they're not in phase with one another at every point in space. But what you notice is that the pattern gets better. Not only are the pink ones in a line, but the blue ones are also in a line, and the blue ones are halfway in between the lines of pink ones. Once you have the pink ones laid down, the blue ones go pretty.
Constructive?
Yeah, blue is where constructive is happening. It's where peaks are meeting peaks or where troughs are meeting troughs. You guys can see the contrast between pink and blue there, right? Some people say yes, some people say no. Let me see if I have something that's a more convincing color than blue. You guys feel better about purple? Little purple circles around my blues? I want to be nothing if not convincing. All right, so I guess just to make sure that for anyone who can't see it clearly for lack of contrast on my screen, I've circled all the blue ones now, okay? So we got dark ones and we got light ones. We got this array of stripes, and actually I think it's looking kind of beautiful. Well, we did blue dots, and then I put a circle around them, and that's where constructive interference is going to happen. Now, if I extend this pattern outwards, and hey, I think I'm going to use a Presto card. Presto card. Take Metrolinks. And what I want to do is I want to draw lines, connect the dots. You know, this isn't a graph, but it is sort of a schematic of waves. I'd like to draw lines that go through all these dark ones. I don't want to extend the lines any further than that dark line at the top of this drawing area. I think, well, what do those blue dots with circles around them mean? They meant constructive interference. Okay, well, so constructive interference means the waves are getting high. And what I want to propose is that if these were water waves and this was the wall of a bathtub, see this rectangle at the top? This is the wall of a bathtub, if you like, okay? And let's just say we had something that was making intermittent splashes at the same rate at two spots separated from each other. What would the ripples look like up on that wall? Well, it seems like if constructive interference is happening wherever the waves smash into the wall along those lines, that means that there would be a peak here. There'd be a peak here. There'd be a peak here. A peak here. Here. Does that make sense to you guys? I would get a peak, a constructive interference thing. There would be lots of waviness at that spot. There'd be lots of waviness at this spot, at this spot, at this spot. And if I sort of extend this idea of drawing lines, notice that if I were to draw the lines for the pink arrays, I'll do them in red. Maybe I'll do them in pink. What the heck? Just extend that line that way. Extend that line that way. And like that. Where those pink lines land on the side of the bathtub, I would expect destructive interference. Well, what does destructive interference happen or mean? It means no wave movement. It means dead spots. What that means is the wave wouldn't, or the water level wouldn't go up and down at all at these spots, but the water level would go up and down quite a lot at what I'm calling my maximum spots. Because that's what constructive interference means. It means a lot of wave movements. Remember standing waves from back in the day? Lots of wave movements. And if there's points in space where there's lots of wave movements, we call these guys the antinodes. And we call the spots where there's barely no wave movement, we call these guys the nodes. Now, because this is a symmetrical situation, you notice that this antinode here is in the middle. I'm going to call this point 0. But because it's a symmetrical situation, I would have node 1 on this side, but there'd also be node 1 on this side. We're just talking symmetry here, right? This would be node 2, and then there'd be a matching node 2 on that side. There'd be a node 3 on this side, and a matching node 3 on this side. Now, I'm going to put up a simulation in a minute, but this is sort of our static drawing version of this, okay? Oh, I should say, if this wasn't a bathtub, if these really are light sources, then we're saying that this is our screen that we're projecting light onto. So if we're leaving behind the analogy of the bathtub and moving towards the idea of what we're really talking about here, that would be the screen we're projecting this image, I suppose, onto.